So last time we stopped at the discrete logarithm problem, and which basically said, just a reminder, G problem, fixed cyclic group of order Q and a generator G, fixed cyclic group of order Q and generator G, and in that case, if it is the generator, we know that every element is of the form. We know that the group generated by G, which is G0, G1, dot dot dot, Gm, well, sorry, in this case Q minus 1, is equal to G, right? Then if it is all generated by G, then given any H for any H belongs to G, there exists a unique X belonging to ZQ such that G to the X is equal to H. Okay, and then we define log G of H to be this X. Okay, and this is the discrete logarithm problem in group H. So this is called the discrete logarithm of H with respect to G in the group G. Now, some of you might be wondering, why are we doing group theory all of a sudden in the middle of cryptography? And the reason is, so far you have seen the easier part of cryptography. Yes, even though it might seem like, oh my god, all these constructions were so hard, that is still the easier part of cryptography, in the sense that is private key cryptography. You are talking about things that you're sharing with someone, and someone can maybe eavesdrop. The person does not have your key. They should not be able to figure out. The key needs still to be transported somehow safely before and stuff. How do you encrypt if you're talking to a random stranger somewhere who does not have some way of accessing you prior to the exchange, so that you cannot give him a key or something? How do you make sure your conversation is safe in that case? And that is where all of number theory and group theory comes in. Let's get to it slowly. Let me just give you a small example that we saw before in Z11 star. Let me take a smaller example this time. Different example. Z7 star. What is log 2 of what is log 2 of 6? Okay, well, what does 2 look like? Well, 2 is equal to 1, 2, 4. Well, my bad. Maybe 2 doesn't even generate this group. 3 does, I think. 3. Right. So, 1, 3. 3 squared is 9, which is mod 7, 2. 2 threes are 6. 6 threes are 18, which is 4. 4 threes are 12, which is 5. 5 threes are 15, which is 1. And we have the entire group 1, 2, 3, 4, 5, 6. Right? Therefore, this says that log to the base 3 of 6 in this group is equal to 1, 2, 3. 3. Okay? What is where did we go? What is the same thing in Z11 star maybe? What is what is log to the base 3 of 6? Well, offhand I don't know if it generates or not. I'm going to hope it does. 1, 3. 3 squared is 9. 9 threes are 27, which is mod 11, 22, so 5. 5 threes are 15, which is 4. 4 threes are 12, which is 1, so this does not generate the group. And, well, so not every group has the same log to the base of every other thing. So, for example, so let me just say, in Z11 star, what is log 3 of 6? As we just saw, I shouldn't have deleted this maybe. 1, 3, 9, 27, so 5, 4, 3s are 15, which is 4, 3s are 12, which is 1. So log 3 of 6 is not defined, Okay? So this need not always be defined. It's defined only when 3 is a generator. 3 is not a generator. Is not a generator. Not a generator. Okay? It's not very easy to tell if a number is a generator or not. Okay? Generator. So you need to be given the generator. What is the discrete logarithm problem? Discrete logarithm problem. Informal. Informally, this said, given in G, D-log problem in G, D-log problem in a group G was given generator G and element H and compute log G of H. And we had talked that we said that on some groups it is easy, on some groups it is hard. So the assumption we are taking is that it is hard. Okay. Formally, let me just remove the informal. I'm skipping some things because we have talked about this before. Assumption on G, D-log problem is hard. Okay. So formally, what is the thing? Let G be a let G be a group generation algorithm. Okay. On input 1 to the n, on input 1 to the n, output a description, description of a cyclic group G. Its order Q with order of Q is equal to n. And a generator G. Okay. For algorithm A, define the following experiment. Define experiment d log a g of n as follows. Compute g q g once you have fed the group generation algorithm 1 to the n. Choose uniform h belonging to G. Run a g q g h to get x. Experiment evaluates to 1 if g to the x is equal to h, right? And we say the discrete logarithm problem is hard with respect to the group generation algorithm G if the discrete logarithm problem is hard relative to G if for all PPT algorithms A, algorithms A, the probability of the algorithm succeeding if n is equal to 1 is smaller than or equal to n, which is negligible in the order of n. Okay. Now, before I move on to the Diffie-Hellman problems, let me give you an example of what it means by the problem is hard relative to G. Okay. On the exam, I asked you the question, find a abelian group G generated by A comma B with A cube is equal to 1 and B squared is equal to 1. Is this group cyclic? The question is, it was hard for you guys to find the group and find whether it's cyclic. But if I had given the same group in another fashion, it would have been extremely easy to see Oh, if it's cyclic or not. Let us see what happens. Because the group is abelian, because G is abelian, A-B-E-L-I-A-N, A times B is equal to B times A. That is the definition of abelian. Okay? Therefore, A to the I, B to the J, multiplied by A to the L, B to the M is equal to A to the I, A to the L, times B to the J, B to the M, which is equal to A to the I plus L, B to the J plus M. Okay? I know A cube is equal to 1, B squared is equal to 1. So the maximum power, maximum power of A is equal to 2. Maximum power of B, power of B is equal to 1. Therefore, the group looks like 1AB, A squared. Let me just write it like this. 1A squared, B, AB, A squared B. With multiplication given by, given by this. Okay, so this is my group. There are 6 elements. Okay, therefore order of G is equal to 6. Question is it cyclic? Well, obviously I can't generate A squared 1, so that does not generate B. B squared is 1, so I can't generate A. What about AB? Well, AB times AB is equal to A squared B squared, which is equal to A squared times 1, which is A squared. Huh. A times B cubed is equal to A cubed times B cubed. Now, A cube is 1. B cube is B squared times B, which is 1 times B. So this is just B. AB to the 4 is equal to A to the 4 A to the 4, B to the 4. Right? This is going into more details than I expected you to show. A to the 4, B to the 4, which is A times A cube times B squared times B squared, which is, well, all 3 of these are 1, so this is just A. AB to the 5 is equal to A to the 5, B to the 5, which is equal to A squared times A cube times B squared times B squared times B, which is, all of the middle terms are 1, so this is A squared B. Therefore, AB generates the group G. In other words, this is same as Z6 is equal to 0, 1, 2, 3, 4, 5, where you can look at things as G is equal to AB to the 0, AB to the 1, AB to the 2, AB to the 3, dot, dot, dot. Well, AB to the 4, AB to the 5. Okay? Discrete log problem is really easy in Z6. discrete log problem is trivial in Zn, right? If the generator is, for example, generator is 1. Generator is 1. Discrete log of n. Discrete log n of 1. Discrete log 1 of n is just n. However, when the group is defined differently, however, when the group is defined differently, right? The problem can become much harder. The problem can become much harder. So for you guys, it might have been hard trying to figure out whether G is cyclic or not. If I had given you the group Z6 and asked you, is this group cyclic? Is this group cyclic? The answer is, of course, yes. It's really trivial to see, right? The extra hidden thing that, oh, I am saying it is generated by A and B, and it has A cube is equal to 3, A cube is 1, and B squared is 1. That makes it harder, right? Now, let us look at what is the Diffie-Hellman problem. Diffie-Hellman problems. Okay. Diffie-Hellman problem says fixed cyclic groups, cyclic group G, and a generator G. Generator G. I am going to define dH of G, Diffie-Hellman of G, as of H1 comma H2 is equal to, well, H1, suppose H1 is G to the X, H2 is G to the Y, then Diffie-Hellman is G to the X multiplied by Y. Okay? For example, in Z11 star, as we saw last time, not this lecture, I did a different example. The group generated by 2 is the generator of Z11 star, and the group looks like 1, 2, 4, 8, 5, 10, 9, 7, 3, 6. So the question is, so what is Diffie-Hellman of 2 of 7 comma 5? Okay. Well, Diffie-Hellman 2 of 7 comma 5 is Diffie-Hellman 2 of 2. 7 is 1, 2, 3, 4, 5, 6, 7. 2 to the 7. 5 is 1, 2, 3, 4. 2 to the 4, which is equal to 2 to the 7 times 4, which is 28, which is equal to Well, what is the value of 2 to the 28 in Z11? Order of Z11 is 10, so this is equal to 2 to the 8 mod 11, which is equal to, well, what is 2 to the 8? 2 to the 8 is 3. So this is equal to 3. Okay? So this is called the computational Diffie-Hellman problem. Okay? There is another way to frame this. In Z star 30920911139, which I don't know if it's a prime or not. I'm going to hope it's a prime. Oh god. What is Diffie-Hellman? Again of 2, which somehow I know is the generator, of 16, 56, 7, 5, 5, 7, 4, 2, and 9, 3, 8, 6, 4, 0, 6, 6, 3. Well, I don't know. Well, let me give you a hint. Is 994993011 the answer? The answer. Or is it just a random element of Z star 30909, whatever the number was, 2091139? Question mark. Okay? And if you can answer this nicely, yes or no, that is bad because this should be a hard problem. And this is called the decisional Diffie-Hellman problem. Okay? So, Diffie-Hellman assumptions. Diffie-Hellman assumptions. Computational Diffie-Hellman problem. Computational Diffie-Hellman problem. I'm going to now just call Diffie-Hellman as DH. Okay? Given G H1 H2, compute DHG H1 H2. That's the computational Diffie-Hellman problem. What is the decisional Diffie-Hellman problem? Decisional Diffie-Hellman problem, which is called DDH. Well, given GH1, H2, distinguish DHG of H1, H2 from a uniform element of G, right? You should already see that, oh, decisional problem is nice because that sounds like I can write what do you call? I can create a distinguisher if it can distinguish dg and dh g h1 h2 from a uniform element. Okay, and that is the idea of the DDH problem. Let G again be a group generation algorithm. Group generation algorithm. Okay. On input 1 to the n, outputs a cyclic group G. Its order Q. Order Q with size of Q equals n, and a generator G. Okay. By the way, this means when I've been saying size of Q, this means length of Q. Q is 2 to the n is n bit long. N bit long. Okay. That is what it means. So given an n, Q is huge. Okay. The DDH problem is hard relative to G. Relative to G if for all if for all probabilistic polynomial time algorithms A, the probability that A G Q G G to the X G to the Y G to the Z is equal to 1 minus the probability that A outputs for G Q G G to the X G to the Y G to the XY is equal to 1. This probability should be smaller than or equal to epsilon of n, where epsilon of n is a negligible function. Okay? Basically, there should be no reliable distinguisher who can say, oh, yes, this is actually G to the XY. It should not be able to separate it from just an arbitrary element. Okay? Once again, relative to G. All of this is relative to the group generation algorithm. And this is a bit easy to see. If the group, if the if the discrete logarithm problem is easy, problem is easy. So is CDH problem. Right? If I can easily find out the discrete logarithm, then I can actually compute the discrete logarithm pretty easily. Right? not a discrete logarithm, the Diffie-Hellman problem. And if I can compute the Diffie-Hellman easily, I can distinguish the Diffie-Hellman easily. If CDH problem is easy, is easy. So is the DDH problem. Well, is the DDH problem, right? This means, i.e., the DDH problem, the DDH assumption is stronger than CDH assumption. Is stronger than CDH assumption. Assumption. Okay. That is, if a group is DDH strong, then it is automatically CDH strong, and it is automatically, in that case, discrete logarithm strong. The CDH problem assumption is stronger than the D-log assumption, right? So me saying that, oh, the discrete, the DDH problem is, and the DDH assumption is strong, this is impossible to do it for this group generation algorithm, means the other two problems are harder as well. Okay. As I mentioned before, the discrete logarithm is not hard in all groups. It is easy in Zn, right? As mentioned before, the log problem is not hard in all groups. All groups. Okay. I said that if the generator is 1, it is easy. In fact, it is, for example, it is in fact easy for all generators of Zn. It is easy in Zn for all generators. Basically, what are you trying to find? You're trying to find some element M such that d log in Zn, d log A of B is x such that x times A is equal to B, right? Mod n, i.e. x is equal to B times A inverse mod n. Which is not hard. Computing A inverse is not hard given in n, and so this is a really easy problem for any generator, not just one. Okay. Nevertheless, there are certain groups where the problem is believed to be hard. to be hard. Note, since all cyclic groups are isomorphic, since all cyclic groups are isomorphic of the same order, cyclic groups of the same order, are isomorphic. The group representation matters. The group representation matters. Okay. What is isomorphic? Definition. It is an extremely important definition. I'm not sure how often we'll be using it, which is why I didn't define it before, but it is an extremely important definition in terms of group. G1 with an operation I will call composition 1 is isomorphic to G2 with a composition O2 if there is a map F from a map phi from G1 to G2, G1 to G2, satisfying first phi of 1 in G1 is equal to phi is equal to 1 in G2. Okay. And second, phi of phi of G. Okay, let me do this. Let me call these groups G and H, just to make life easier. G and H. Okay. From G to H, satisfying three conditions. 1 of G is 1 of H. Phi of G when composed G H composed G H of G2 is equal to phi of G1 composition in H phi of G2. So the operation should go through. The operation in one should be the same as the operation in the other, and 3, the map should be 1 to 1. The map should be 1 1. Okay. Now, it follows from property 2 that property 1 and 2 that phi of G inverse is phi of G inverse. Okay. Example, G is equal to 1a squared b ab a squared b with multiplication is isomorphic morphic to Zn is equal to 0, 1, 2, 3, 4, 5 with 5 from G to H being given by phi of G is equal to d log G, d log AB of G. Okay, homework. Check this is an isomorphism. Check this is an isomorphism. Okay. So clearly it is important to choose the groups properly. Okay. For cryptographic applications, so groups selection. For cryptographic applications, there are two kinds of groups that are really good. Okay? For cryptographic applications, best to use prime order groups. Okay. There are reasons. First, the D-log problem is easy. D-log problem is easy. It becomes easier if the order of the group has small prime factors. There are algorithms which allow you to do this. Okay. Second, prime order groups have several nice properties. The most important of which, for example, is that every element except identity is a generator. Okay. So there are two common choices of groups. There are two common choices of groups. Okay. Choice one. Choice one. Prime order subgroups of ZP star P prime. Okay. So for example, let P is equal to TQ plus 1 for Q prime. Okay. take another prime q for which p is t times q plus 1. Take the subgroup generated by the subgroup of the tth powers, i.e. g is equal to x to the t mod p, given that x belongs to zp star. Okay, now note there are certain properties which we haven't proved. I mentioned something else, but this is also true. This is a group. This is a group. That's pretty easy to see. If you take elements a and b in this, then a has to be x to the t, b has to be y to the t, then a times b is x times y to the t. Since we are dealing with cyclic groups, they're abelian. A times b, a to the t, x to the t times y to the t is xy to the t. Right? So it's easy to see that this is a group. But also the identity is there because 1 to the t is just 1. Right? What is important is that it has order p minus 1 over t, which is q. Okay? And since q is a prime, prime, this group must be cyclic. The group must be cyclic. Okay. Note we have discussed, we have seen the map x to the e is 1 1 if and only if GCD of e comma m is equal to 1. X to the t in this case is not 1 1, as t divides phi of p is equal to p minus 1 is equal to t times q. Okay, in this case now this I'm going to say without proof. Okay. Every it's a t to 1 map. It is a t to 1 map. Okay, for example, so exemple gratia, e.g. Z7 star well, look at the map. X goes x cube in Z7 star. In your exam, you have to show that x cube is actually 1 to 1 for some group, Z15 star. For Z7 star, 7, 3 divides phi of 7, 3 divides phi of 7, which is equal to 7 minus 1, which is 6, which is equal to 3 into 2, right? So it's not 1 to 1. So not 1 1. It is 3 1. it is 3 to 1 map. Okay, three things in the bottom get mapped to 1. So let us look at it. What are the elements of Z7? Well, Z7 star 1, 2, 3, 4, 5, 6. These are the elements of Z7 star, right? Let us look at their cubes. 1 cube is 1. Okay. So let me do this. X cube. 1 cube is 1. 2 cube is 8, which is also 1. 3 cube is 27. And what is divisible? 28 is divisible. 21 is divisible, so this is 6. 4 cube is 64. 63 is divisible. 1. 5 cube is 125. 126 is divisible because that's 140 minus 14, right? So 18, it's 14, 8 is 126. So this is 6. 125 gives it 6. And 6 cube is 216. And 210 is divisible by 7. So that is 6. So there are 3 things that are mapped to 1 and 3 things that are mapped to 6. Right? So it's a 3 so it's a 3 to 1 map. Okay? That is why this map is 3 to 1, and the order of elements is so the group let me actually, these are the wrong brackets. Should be equal to just 1 comma 6, cardinality of which is equal to 2 is equal to q. Okay. So you have this. You can generalize this based on finite fields. Finite generalizations based on finite fields are also used. This is a whole another mess. I'm not going to go into that. The second choice 2, which is what is nowadays starting to pick up pace for what should be used, and this is more or less the future of cryptography, and this is where the more strength of cryptography is coming from in today's thing. This is what is the push towards that. This should be what is used, is prime order subgroups, order subgroups of an elliptic curve group. Curve group. Okay. Let me just write it here. There was no need for me to go separately. Choice 2. This. And this is a whole another beast. This is a proper full course in graduate school, elliptic curves. Okay. So I am not going to go into that one. That is extremely troublesome. But yeah, so I'm not going to go into that. We will look at next time. We will describe algorithms in abstract groups. What is an abstract group? You're describing the group using the properties, the same way that we did for AB. right? For the group G, I described the properties. I don't know the full properties of the group. I have to find them, right? That is what it means by abstract group. Okay, can ignore details of the underlying group in the analysis of the underlying group in the analysis. Okay, and can instantiate any appropriate group for an implementation. Okay, so we'll look at that next time. I'll stop this one here.